Let us start with a set with some extra features, like these features. And these restrictions on a set defines a mathematical structure. If our set has some sort of topology, then it is known as topological structure with information of continuous deformations. Whereas if our set has some finite collection of operations, then it is an algebraic structure, and a group is a very famous example of it, dealing with the symmetries. So these two structures exist independently and has their own importance. What if our set has both of the structures? Then it becomes a combination of these fundamental concepts of groups and topology, storing the continuous symmetries known as topological groups. Let us see some mathematics behind them. Let G be a group with a binary operation star, where tau is a topology on G. If we have a multiplicative map from G cross G to G, defined as if for two elements it is just a multiplication with respect to the binary operation. And we have an inverse map I from G to G defined by that if any element is given to it, it will give its inverse. And if these two maps are continuous, then G is a topological group. We have another similar kind of definition for topological groups. It's a map F that possesses the properties of multiplicative and inverse map. Instead of checking continuity of both, we can check the continuity of F only. To make the concept clear, let us start with our main example of S1 and let us prove it a topological group. So the set S1 is actually a unit circle in the complex plane, and it is a group under multiplication. The topology on S1 has the basis element defined by the set B where epsilon is greater than 0, and it is actually representing the open arcs on the unit circle, as you can see in the figure by dash portion. So we are aware with all the terminologies. Now we can start our proof. So I am going to use the second definition of topological group in the video I have discussed before. So let us take the function f defined by this, where x and y are the elements coming from the group S1. To make S1 a topological group, we have to show that this function f is continuous. And using the criteria of continuity in topology, we have to show that for xy belongs to U, an open set in S1, we will find f inverse of U that is open in S1 cross S1 in the product topology containing the tuple xy. Now let us make things more clear, as x and y are coming from the group S1 and S1 contains the complex numbers on unit circle. So with a radius equals to 1, x and y can be represented in their exponential form, where multiplication is the binary operation here and it represents only the addition of angles. So x multiplied by y inverse is actually, for xy inverse, there exists a basis element defined by set B for epsilon greater than 0, and it contains xy inverse, which is obviously contained in the open set U. The set B here exists and this inclusion holds because of the theorem that for any x in any open set U, there exists a base element containing x and it is contained in U. Moving towards, we reached at a similar argument that as x and y are coming from S1, then there exist basis elements b epsilon by phi epsilon by 2 and b theta epsilon by 2 such that if we apply the function f on the tuple xy, then we have arrived at this inclusion. Now if we apply f inverse on this inclusion, then we have arrived to this, where the set is actually a basis element in the product topology of S1 cross S1, and it is contained in F inverse of U. So this implies that F inverse of U is an open set containing the tuple xy. Hence, F is a continuous function from S1 cross S1 to S1, which completes the construction, and by definition of topological group, S1 is a topological group.